whether you are taking the SAT or taking the Olympiads or somewhere in between. Meniner theory may come of use to you. This is Andy, and this is Meniner theory, formulated by me and a bunch of people from AwesomeMath. And here we have a simple abstract that you can read of how Meniners can simplify harmonic operations, parallel rates, reciprocal sums, and aid your journey through math and physics. Before we define the core theorems of Meniner theory, we must first define what we're actually talking about. The unnoted Meniner, by convention, is just the number of the Meniner itself. Hence, we typically do not have to write the M for Meniner. However, when Meniners are not explicitly used in the problem, it will be more useful to write them in this form to make sure the reader knows that you are using Meniners. The noted operation can only be used on unnoted Meniners and is equal to the reciprocal of the sum of reciprocals of the Meniners. For example, the noted Meniner object of A, B, and C will be 1 over A plus 1 over B plus 1 over C. Okay? And this is the definition of the noted operation. We shall now move on to one of the most important theorems of all Meniners, which is the Fundamental Theorem of Meniners, which says noting Meniners in any order and in any permutation does not alter the final result and is strictly equal to noting all of them simultaneously. Meaning, as an example, noting 2, 3, and 6 is equal to noting 2 and 3, and then taking the entire thing and noting 6 again. And that can sort of prove that Meniners are associative and commutative, right? So, that is the idea of the Fundamental Theorem of Meniners. And here we have a very simple proof. We will not show it here because the proof is way too simple. It is left as an exercise for the watcher. Now, the identity theorem of Meniner states that the identity Meniner infinity noted with any Meniner leaves the original Meniner strictly unchanged. And this can be shown here. Noting A with infinity is 1 over A plus 1 over infinity to the negative 1, right? And as 1 over infinity is 0, the expression becomes 1 over A plus 0 to the negative 1, which is an A to the negative 1 to the negative 1, which becomes A, right? So infinity is the identity element. And we can also show that there is an inverse element for noted Meniners, which is negative A, because 1 over A plus 1 over negative A to the negative 1 power, this is by definition of what the noted operation is, yields 0 to the negative 1, which is infinity by convention. Therefore, negative A is the inverse of A under the noted operation. And here we can define a noted Meniner group, which is closed by the noted operation, which, again, we will not show here as it is not that important for Olympiad or SAT problems. It is useful, however, for discovering new theorems because most theorems are based off the fact that this group and ring exist. Similarly, we can prove that the noted operation has a ring. Again, we will not show this here. Feel free to discover it for yourself. We can also prove that the Meniner of all of these terms is equal to the nth symmetric sum to the n minus 1 symmetric sum. And this allows us to yield the following formulas for 2 Meniners, for 3 Meniners, and for 4 Meniners. And these will be useful for calculating 2, 3, or 4 Meniners together. And then we have a few theorems, right? The Bret3 Lemma states that for a set of n independent agents working together, let's say we have 4 workers, and if they each take t to finish it, let's say the first worker takes 2, the second worker takes 3, the third worker takes 5, the total time is equal to the noted operation of all of them. In a similar manner, if we have a bunch of resistors, the equivalent resistance of this parallel group is in fact equal to the noted operation of the three resistances R1, R2, and R3. And this is another application of the Bret3 lemma. The Paektu lemma states something relating to solving noted Meniner operations and solving noted equations. We will show how to solve noted equations later, so the Paektu lemma is not needed for now. And it is also very crucially tied to the idea of the flat Meniner, which we have not discussed yet. The Jagmag theorem is an extension of the Bret3 lemma, stating that if an agent K reverses a task in time tk, the agent can be represented as an anti-Meniner with value negative tk. And the total time remains consistent under the noted operation. And the proof is by the negative Meniner lemma, which we will not cover. The Kleit's theorem states that if an object traverses n sequential intervals of equal distance, and this can be generalized by weighted Meniners, but the Kleit's theorem is also very useful on its own. Its average velocity is n times the noted operation of all the velocities. This is when we have back and forth movement like this, we have equal distances traversed. And this does not actually depend on d itself, the distance that it's traversing. So this is very useful, Kleit's theorem. And weighted Meniners are very useful for Kleit's theorem generalizations if we have different intervals of distance. But we'll show a few examples. First of all, 2, 3, and 6 hours. Usually you'll have to solve a very annoying reciprocal equation. Here, we can just use either the noted operation on all three, right, or the fundamental theorem. So in the bottom, we have a solution with fundamental theorem where we note 2 of them at once, and then we note the other 2 at once. There is also another solution just by using the symmetric sum idea, right, which gives us 2 times 3 times 6 over 2 times 3 plus 3 times 6 plus 2 times 6, and that's 6, that's 18, that's 12 here, right? And then these sum to 36 over 36, and that's just 1, right? So this is another way of solving it without using the fundamental theorem. Here we use the Jagmag theorem. A pumpkin filled a water tank in 4 hours. A leak can empty the water tank in 12 hours. How long will it take to fill the tank? And then we just assume, using the Jagmag theorem, that the leak takes negative 12 hours to fill up the tank, and we can solve using the noted operation. And here we also have 15 days, 10 days, and negative 30 days. Noting these three, we can just use the fundamental theorem, and we note 15 and negative 30 first, then note 10 and 30, yielding 7.5 days. These are all very trivial applications. And before we move on to the Baltic Way problem, which is from a recent Baltic Way, by the way, it's a problem 5, which means it's relatively hard. We need to first define the flat operation. And the flat operation is used to solve noted equations and Meniner equations, and it extracts a unknown unnoted Meniner. So it's the reverse of a noted Meniner, similar to how logs are the reverse of exponents. And we can see here, if we have m note of a and b is equal to t, and we know t and we know a, if we want to find b, we must use the flat noted operation, right? And here we can see that m flat of a and t is just at over a minus t for 2 variables. The flat operation will be slightly different for more variables, but essentially for more variables, you note all the ones you know, and then you do a 2-variable flat operation with the one you don't know. Now here we can see that we are writing numbers on a blackboard here. Okay, yeah, there we go. There's the highlighter. You can see that we are writing numbers on a blackboard where m is greater or equal than to 2, and a move consists of writing this down on the blackboard using 3 numbers a, b, and c. And we can show, very trivially, that this is the 3-variable noted operation on a, b, and c. And then by the fundamental theorem of noted Meniners, the total note is invariant under this move idea, right? And then we expand out the total noted operation. We telescope, right? These terms telescope, these terms telescope, these terms telescope, right? And all the terms telescope away to yield 2m over 2m plus 1. Remember that the noted operation requires us to flip it, and we finally yield this as the invariant noted Meniner. And then we know that two numbers remain, using the flat operation, we know that the other number is m flat of 4 over 3 and t, because we know the total noted Meniner is 2m plus 1 over 2m. And using the flat definition, we solve for b being am plus 4 over 2m minus 3. And to show b is greater than 4, we can take b subtract 4, or you can just factor out take out a 4 from this, and then see if there's any negative annoying things. But essentially, we're just evaluating the difference, right? And then we see that the difference is, in fact, positive because m is greater or equal than 2, given by the problem. And then we strictly prove that the other number is greater than 4 because the other number minus 4 is a positive number. And that allows us to prove a 2019 Baltic Way problem 5 from one of the most notoriously hard Olympiads in the world. And here we are trying to prove a 2014 Junior JBMO Shortlist problem from Combinatorics 1. And here it's essentially telling us we note 2, and then we want to prove that the last number is invariant. And this is probably one of the most trivial problems you can solve using notes and Meniners. And you can now say that you can solve a 2014 Junior JBMO Shortlist C1 in 2 lines. The first line states that this operation is just a noted operation. The second line uses the Fundamental Theorem of Notes and Meniners, and we are done. And so therefore, you have just proved a 2014 Junior JBMO Shortlist Combinatorics problem 1, and you can show off to anyone you want that you know Meniners, and you can solve the problem with Meniners. And so therefore, this shows and demonstrates how complicated problems can be solved using just a simple framework of notes and Meniners. And I hope this will be of use to all of you SAT takers and all of you contest preparers, because notes and Meniners really are something else. And I hope one day more and more operations and properties can be discovered of Meniners, and more problems requiring invariants and requiring inequalities can be solved using Meniner theory. Thank you, and see you on the other side.